Alrighty, folks, so this is week 2 problem session. And so we got a nice turnout on the discussion post. Still not everybody doing it. Remember, this is part of your participation grade, just in case you're watching this and not doing the rest of stuff. But putting at least 2 problems on the discussion board for each week's problem session is most of the participation grade. So if you haven't been doing that, I would suggest looking for a couple that you'd like to see. I also note that on the board there was nothing from section 2.5, and that might very well be because 2.5 seemed easy and nobody wanted help with it, but I do also want to remind folks that it's usually 3 sections per week, right? The first week was different because we had a syllabus day instead of a section, but it's usually going to be 3 sections a week. So I just wanted to make sure that was clear in case that's why there was no 2.5 questions. And it also could have been because y'all decided before Friday and just did 2.5 on Friday. Either way is fine. But let's hop into problems. We're going to start off with the ones from 2.3. Right, and so the first one that there was a question asked about was number 18. All 3 of the problems from this section involve using the limit rules, which makes sense because 2.3 was all about the limit rules. And the first 2 are explicitly just use the limit laws. So it's asking us to find the limit as w goes to 7 of the square root of w plus 2 plus 1 all over the square root of w minus 3 minus 1. Right? So the first thing we can do is we can use the quotient rule to say that this is the limit. And I'm not going to write the w going to 7 each time. I hope that's not too confusing, but I'm going to be writing this a lot of times, so I'm going to leave off that bit. This is the same all the way through. All right, and now on each of those limits, I can use the sum or difference rule, right, to say this is the limit of the square root of w plus 2 plus the limit of 1. So that's using the sum rule, and using the difference rule, we get the limit of the square root of w minus 3 minus the limit of 1. And now we can use the rule that the limit of a constant is just that constant, right? So that doesn't really have a name. We'll call it the constant rule. Right, so that says we can write this as the limit of 1 is just 1, and the limit of 1 is just 1. So there we go. The next rule we have is the power rule. And that might seem a little bit tricky here, but we got to remember that roots are just powers, right? Square root is raising something to the 1/2 power. So that means that we can take the limit inside of that square root. Right? Basically, we raise the limit to 1/2 instead of what's inside the limit. Right? And next we can use the sum and difference rules again. So that's going to be the square root of the limit of w plus the limit of 2 in square root, and the square root of the limit of w minus the limit of 3 minus 1. And here we have to use another pair of rules that don't have a name. First, we're going to use the constant rule again. Right, so we'll go ahead and get that one done. It's going to be the square root of the limit of w plus 2 plus 1 all over the square root of the limit of w minus 3 minus 1. Now, the other rule that we have that doesn't have a name is that the limit of the variable, just the variable by itself, that's it. So in this case, the limit of w as w goes to 7 is just whatever it's going towards. So we'll call this the variable rule. So that means we're going to get the square root of the limit of w as w goes to 7 is 7. The limit of w as w goes to 7 is 7. And now we can just simplify. No more limit rules. Right. Righty. So that was pretty much breaking it down. I really only did multiple things at a time when they were the same type of rule, like the sum difference rule. But we can skip a little bit, right? So if we do problem 21, this was the limit as t goes to 25 of 3 square root of t minus 1/5 t. Right. So we use the quotient rule again. Right, and here I'm going to use the difference rule up top, and I'm going to use the power rule on the bottom to get the limit of 3 root t minus the limit of 1/5 t all over the limit of t minus 20 squared. So again, I'm going to do these sort of by top and bottom. On the top, I'm going to use the constant multiple rule. And I'm going to use it twice, right? That says that I can pull that 3, because 3 is a constant here. And I can pull out that 1/5. And on the bottom, I'm going to use the difference rule. So I'm going to get the limit of t minus the limit of 20. And both of those are going to be squared. Right. So next, I'm going to use the power rule and the variable rule up top. And I'm going to use the variable rule and the constant rule on the bottom. So I get 3 times the square root of the limit of t minus 1/5. T was going to 25. So limit of t as t goes to 25 is 25. All right, again, the limit of t as t goes to 25 is 25. And the 20 is a constant, so it just gets there. So here, I'm going to use the variable rule again, and then I'll be done with limits. And the rest, I'm going to simplify. get 10 25ths, which is 2/5. Right. Now, in the next couple sections, we learn ways that we don't have to take quite as many steps. But for these problems in this section, this is what they were wanting you to do, is understand why all of these powers work like this, and it explains why we can do substitution in cases like this. Right. And the last one from this section was 26. And here was a little bit trickier because we don't actually know what the function is, but we know that the limit as x goes to 6 of f of x equals 4. Right? So this is sort of going to replace our variable rule, right? Because usually we would say, okay, if we see x, then when x goes to 6, x is going to be 6, right? Whereas here, we're never going to see x, we're just going to see f of x. But instead of knowing that x goes to 6, we know that f of x goes to 4. So the first part of this problem was asking what's the limit as x goes to 6 of f of x squared. And so that means we need to use the power rule. So we get the limit as x goes to 6 of f of x and all of that squared. Now we're going to use this fact to say that that's 4 squared, and we get 16. So the next part was the limit as x goes to 6 of 1 over f of x. All right, so we're going to use the power, or the quotient rule rather. Power rule was last time. To get that that's the limit as x goes to 6 of 1 divided by the limit as x goes to 6 of f of x. Right, and so that's going to be the constant rule. And it's going to be this rule again. So up top, we're going to get 1. Because that 1 doesn't care what x is going to, it's going to stay what it is. And we know that the limit as x goes to 6 of f of x is 4. So we get 1/4. And lastly, part C, the limit as x goes to 6 of x times the square root of f of x. So this one we actually have an x here, so we're going to get to use the variable rule again. But first we're going to need to use the product rule and get that that's the limit of x times the limit of the square root of f of x. We're going to use the variable rule and the power rule to say, well, the limit of x as x goes to 6 is 6, and that square root is secretly a power, so we can put it around the whole limit instead. And then we're going to use this rule to say that that's 6 times the square root of 4, because we know that the limit as x goes to 6 of f of x is equal to 4. So we get 12 out of it. Right. Alrighty, so those were all the questions we had from 2.3. And we had a bunch from 2.4. And for starters, we're going to work on 35. So I'm going to try to flip to that page on my book. 2.4 was all about continuity. So it had the definition of continuity and some laws of continuity. And these first two problems that we're asked about are using the laws of continuity. So we're supposed to determine the domain and show it's continuous there using laws of continuity. Right. So for 35, the function was 2 sine x plus 3 cosine x. Determining the domain is a review thing from pre-calculus, right? That was something we could do then. And if we recall from that, you find the domain of sums, products, quotients, and difference. Well, sums, differences, and products are just the domains of all the pieces put together. Quotient is the domain of that piece plus anything where the bottom is equal to 0 gets thrown out. And composition has its own funky rules that we're not going to talk about quite yet. But if we recall from calculus, sine and cosine have a domain negative infinity to infinity. And so when we add them together, we get the same domain, right? Usually we would be intersecting the domains, but if you have the same domain twice and you intersect them, you get the exact same set back, right? So the domain is everywhere. And we also know that sine is one of the basic continuous functions. Right? There's a whole list of them: polynomials, rational functions, algebraic functions, trigonometric functions and their inverses, exponential functions, logarithmic functions are all continuous on their domain. The constant multiple rule says that, therefore, 2 sine x's, right? Because if we take a continuous function and multiply it by a constant multiple rule says that it's still continuous. Cosine x is another basic function. And the constant multiple rule again says, therefore, 3 cosine x's. Since both of those are continuous, the sum rule says, therefore, the sum of 2 continuous functions is continuous. I should say is continuous. Right. So we started off with 2 continuous functions. We're allowed to multiply them by constants, and it remains continuous. And we're allowed to add them together, and it remains continuous. Right. So the next problem, 42, had the same instructions, but a different function. So that function is f of x equals natural log of 9 minus x squared, right? So if, again, we recall back to pre-calculus, 9 minus x squared polynomials have a domain negative infinity to infinity. And ln of x has a domain of 0 to infinity, not including 0. Right? So that means our domain is given by what's inside the logarithm having to be strictly greater than 0. Right? But domains need to be written in terms of x. So we're going to go ahead and solve this for x. and we get that x needs to be between 3 and negative 3, right? Just if we recall how taking the square root of both sides works for inequalities, we know that if x is smaller than negative 3, then when we square it, it's going to be the same as squaring something bigger than 3, right? Because the squaring makes everything positive. So if we want to be less than 9 when we're x squared, we have to be between 3 and negative 3, right? So that's our domain. And we need to show it's continuous using the laws of continuity, right? So 9 minus x squared is a polynomial. So it's a basic function. ln of x is a basic function. And the composition rule says, therefore, ln composed with 9 minus x squared is continuous. Right? So if we have one continuous function and we put it inside another continuous function, then we're going to have a continuous function. That's what the composition rule says. All right. Let's see. So the next problem takes us a little bit away. We're not using the continual continuity rules anymore. We're using a fact about continuous functions that says that if you have a continuous function, then you can figure out its limit using substitution. So the instructions here were evaluate using substitution. And we were given the following limit. The limit as x goes to negative 1 of 1 minus 8 x cubed to the 3 halves. Right? Now, usually we want to check if it's continuous before we use substitution. But again, we've got a polynomial which is a basic function. We've got a raised to a power. So power functions are also basic functions. And again, using this composition rule, just like we did up here, when we raise a polynomial to a power, that's composing a polynomial with a power function. And so it's composing two continuous functions. So it's continuous, right? So that means we can do substitution. And that means that to evaluate this limit, we just have to take x and replace it with its variable, right? Negative 1 cubed is just negative 1. And that means we add. Right, remember, raising to a fractional power, you can do either piece first, right? So we could write this as 9 cubed. We could write this either as the square root of 9 cubed, or we could write it as the square root of 9 and then cube it. And I kind of like this second one better because I know what the square root of 9 off the top of my head is. And it sounds a lot better than figuring out multiplying 9 by itself 3 times. But either way is fine, whichever one's easier for you to figure out, and we get 27 from that. So the next question was about 81. And that one was sort of a thinking through problem. So it said that f of x and g of x are discontinuous at a point C does that mean f plus g of x is discontinuous at C? Right, and it wanted you to either make an argument for it or give a counterexample if you thought that it wasn't the case. And it turns out it's not the case. So coming up with a counterexample means we get to decide any f that we want and any g that we want as long as they're discontinuous at a particular point, and then we want to show that their sum actually is continuous. So this is going to be hard to draw, but I'm going to try to use colors. So we're going to have f of x be 0 up until we get to C. And then it's going to be 1. And then it's going to be 0 the rest of the time forever. Right? So this function is clearly discontinuous at C. It's a it's a removable discontinuity, rather. We could replace it, but it is still discontinuous. And I'm going to have g of x be almost the exact same function. Right? It's also going to be 0 all the way up to C. But then it's going to be negative 1. And it's going to be 0 the rest of the time forever. Right? So, if we add this, right, so, let me get my black pen back. So f of x is going to be 0 if x is not equal to C, and it's going to be 1 if x is equal to C. G of x is going to be 0 if x is not equal to C, and negative 1 if x is equal to C. And f plus g of x is going to be 0 plus 0 if x is not equal to C, and it's going to be 1 plus negative 1 if x is equal to C. And that, it turns out, isn't even piecewise, it's just always 0. Right? So f plus g is just this function all the way through. And that's definitely continuous. Right? So this is a counterexample to the idea that discontinuous functions, when you add them, are discontinuous. Right? It turns out that if you add two discontinuous functions together, if they play very nicely together, sometimes you get a continuous function out of it. Right? And the other part of the question was, does this contradict Theorem 1, right, which is the thing, Theorem 1, part I, says that if two functions are continuous, then their sum is continuous, right? So the thing about statements in math is that if you start off your statement with if, right, if your two functions are continuous, and that's not true, so maybe your two functions are discontinuous, the theorem just doesn't apply. It's not that it's invalid, it's not that it doesn't work, it's that the theorem only says things if that first thing is true, right? So the Theorem 1 here is not even part of the question, because Theorem 1 starts with if the two functions are continuous. This problem starts with if the two functions are discontinuous. So they live in entirely different worlds, and they can't affect one another. Right. So our next one was to show that f of x equals the absolute value of x is continuous. Right? And the key thing that it helps remember for this one is that the absolute value of x is secretly a piecewise function, right? It's equal to just x if x is greater than or equal to 0, and it's equal to negative x if x is less than 0, right? If you put a positive number in to the absolute value, you just get the exact same number back out. If you put a negative number in, you get the positive version of it back out, and another way to get that positive version is to multiply by -1. Right, and so we talked a little bit in the mini lecture video about piecewise functions. But the trick with piecewise functions is that, well, first off, the pieces have to be continuous. So x and negative x are both continuous. So that means we've got a lot of the checking out of the way. That's almost all of the values for x belong to just one of those two things. But then we have to check the change points, right? So we need to check the places where where we go from one piece to another, right? So specifically in this one, we need to check x equals 0. So for that, to check the change points in a piecewise function, we need to go back to the definition of continuous. So we need, for f of 0 to equal the limit as x goes to 0 of f of x, right? Now, f of 0 is clearly 0, right? The absolute value is 0. So that just means we need to figure out what this is, right? So in a piecewise function, we can't really do it from both sides at the same time. We have to look at, or specifically change points, we have to look at one side or the other. So let's look at the limit as x approaches 0 from the left, right? So if we're approaching 0 from the left, that means we're always going to be negative. And if we're always negative, then f of x looks like negative x, right? We're in this piece. If we're always negative, if we're always to the left of 0, then we look like that piece. And that's continuous, so we can just do substitution and get 0. So that's a good start. Now we need to check the limit as x goes to 0 from the right of f of x. Now if we're at the right of 0, then we're always going to be in this piece, right? Which means our f of x is basically just x, right? But that's a continuous piece, so we can do substitution. These two guys equal, so the limit as x goes to 0, just no sides mentioned, of f of x equals 0, right? So that equals f of 0, so f of x is continuous at 0, right? So it's continuous for anything greater than 0 because x is continuous. It's continuous at 0 because we just checked, and it's continuous at anything less than 0 because negative x is continuous. So, therefore, f of x is continuous. Right. Now, 83 wanted us to use this fact. So, 83 said use number 82 to show that if g of x is continuous, then the absolute value of g of x is continuous, right? Now, if g of x is continuous, we just showed that the absolute value of g of x is continuous. So this is the composition of g of x and the absolute value of x. Both are continuous So f of x is continuous by the composition rule that we used a couple of times up there. Right? Okay, so that was all the problems from 2.4. Hey, and we are out of paper. So we're going to do a couple of problems from the homework. And by a couple, I mean we're going to probably do 3, and there's one we're going to talk about how you would do it. So I'm going to get out of here. Go to part 2. And we're going to work on some homework problems. So this is week 2 problem session, part 2. And this is where we're going to work on some homework problems. So number 1 was asked about, and so a ball is thrown straight up with initial velocity 79 feet per second with the height in feet of the ball after t seconds is given by y equals 79t minus 16t squared. And the problem asks us to find the average velocity for the time period beginning with t equals 2 and lasting, and there was multiple parts and each one of them had a different lasting. So this problem is a lot like some of the ones we did in last week's problem session, because it was from the reading from last week. That's gonna happen a little bit because of the way the homeworks and the problem sessions mesh up. But the first part, part A, was wanting it to last 0.1 seconds, right? So that means that we are looking at the time period 2 and 2 plus 0.1. So we get that guy, right? And average velocity, remember velocity here, when we're talking about a position function, is the rate of change of position. So that's going to be the change in y over the change in x, right? So I plug this into a calculator. And got 13.4. Now the second part said that it was going to last 0.01 seconds. So that means we're looking at the interval 2, 2.01, right? So we're going to do the same formula. We just have a slightly different second one. Right? And plugged all that in. To a calculator and got 14.84. Next one was to be lasting 0.001 seconds, which means we're looking at the interval 2, to 2 plus 0.001. And we're going to plug it into the same formula. We get 94 minus 94.01498 all over negative 0.001. Plug that into a calculator and get 14.98, right? So that's getting all those average rates of change. And we recall that, or the next question is to, or the next part of the question, guess the instantaneous velocity at t equals 2, right? So, the way that we had to estimate the instantaneous velocity in the first couple sections was that we would make intervals that started with the number we care about, or ended with it, either way, and got closer and closer and closer on the other hand. So that's exactly what we've done here. And we know that if we do that, our output should get closer and closer and closer to the actual instantaneous velocity. So looking at these three numbers, if I were doing it on my own, I'd probably do one more just to check. But it really looks like it's going towards 15 here, right? We're getting bigger and bigger, but we started to slow down and we're not getting over 15. So it looks like we're getting closer and closer and closer to 15, which with each of these guys that we have there, right? So number 2 was a similar problem. We're not going to go all the way into it, and actually what I'm going to do is, come on, go away. Here we go. Is do some modifications here. This is another one that's going to work just like this problem, at least the work for it, right? Except that it gives you these, and it's got some slightly different vocabulary. This average velocity is the slope of the secant line. Right? That's just in the particular case of problem 1, the slope of the secant line tells you the average velocity. But what you're actually finding is the slope of the secant line. So in problem 2, when it asks you find the slope of the secant line, you're going to use this exact same formula to find the slope of the secant line. It gives you some specific intervals, and it gives you one that start and end. I think it gives you like 6. It gives you one that start and end at the point that you care about. So you'll want to look at them separately because they tell you the limits on each side. And instead of asking about instantaneous velocity, it asks about the slope of the tangent line. And that's just because, again, problem 2 is a very specific case where we're talking about a position function, and the slope of the tangent line of a position function tells you the instantaneous velocity. So questions asking for the instantaneous velocity and the slope of the tangent line are asking for the same thing. So the whole process and the formula and the way you work it is the same as 1 once you make those sort of translations. Let's see. So I just realized I forgot to write some things down. So let me see if I can get to it. So in this problem, it was asking to calculate it wasn't calculate, it was estimate okay, this is not loading fast enough, so I'm gonna have to, maybe it will be fast enough. All right, here we go. So, having to bring it up right here. We want question 5. So question 5 said estimate the limit numerically, or say it doesn't exist, and it was looking at the limit as x goes to 0 of sine of 21x over x. Right? So estimate the limit numerically. You can, so you have the option, you can do it like that. So you can do it just like that. You'll have to pick your own numbers, right? So you would be doing like 0 and 0.1, 0 and 0 plus 0.01, 0 and 0.01. Wait, nope. I'm messing that up. So you actually, it is like those, but it's a little bit simpler. This is the formula you're plugging into, and you just have to plug in increasingly close numbers to 0. So plug in 0.1, 0.01, 0.001. But I strongly recommend using a calculator that can give you a table. So let's go to the calculator. We want to go to y. We want sine of 21x divided by x. We want to check our table set. We want it to start at 0, because that's the number that we're trying to limit to. And we want this to be pretty small. That's pretty small. Right, so we go to the table, and in this case, we've made things small enough that it's gotten confused and plugged in something really close to 0, and rounded it off for us. But we can see as we go up on from above, right? So this is the limit plus, whoops. And as we go down like this, we're getting closer and closer to 21. These give us the limit as x approaches 0 from the left, and that's getting closer and closer to 21. So looking at that table, all right. So I'm going to have cut some things, but from that calculator table that we were just at, we know that this limit is going to be 21. And looking at the table is what it means by evaluating it numerically. Again, if you don't have a calculator that can make a table of values for you, maybe you're plugging it into Google, then you can just plug in things that get closer and closer. You'll also, if you do it this way, to make sure you get the limit on both sides, you'll also want to do negative 0.1, negative 0.01, negative 0.001, negative 0.0001, right, to try to see where it's going, right? And for problem 6 was very similar. It said use numerical or graphical evidence to determine the limit as x approaches 9 from the left of, well, let's not do 9, let's do 7, of 14 minus 2x all over 7 minus x. And it also wants to find the limit as x approaches 7 from the right of the same function. Right? So numerical means do the exact same thing as above. So we have options. We could plug in, we would be at 6.9, 6.99, 6.999, etc. for A. Right, because those are all numbers less than 7 that are getting closer and closer to 7. And 7.1, 7.01, 7.001, etc. for B, because those are all numbers that are bigger than 7 that are getting closer and closer to 7. Right, so that's one thing you can do. If you're doing something like using Google for a calendar, for a calculator. You could also use a calculator table like the last problem. Or you could graph. Right? So both those last two need a graphing calculator, though Google can do this. If you just tell it to graph a function, then Google can generally graph it for you. So again, if you're using something like Google for a calculator, the graphing one is an option you have as well. So let's see. Here for absolute value, we need to go to math, then numbers, then abs, and it was 14 minus 2x, and this was divided by 7 minus x. And let's look at our table set. We know that we're looking at the limit as x goes to 7, so that's where we would like our table to start. And we want this to be pretty small. So let's look at our table. And of course, we can't get anything when we plug x into 7. But as we get closer and closer and closer and closer less than 7, we appear to be pretty stuck at 2. And as we get closer and closer and closer and closer and closer more than 7, we appear to be stuck at -2. Right? So it looks like the limit as x approaches 7 from the right is going to be -2, and the limit as x approaches 7 from the left is +2, right? So this is one of the numerical ways to do it. We could also look at the graph, and notice that we appear to be pretty solidly at 2 all the way up into x equals 7, and then as soon as we get bigger than 7, we drop down here to -2, right? So we're +2 when we're less than 7, and we're -2 when we're more than 7, and we don't actually, it looks like it has that straight blue bar, but that's just because that's what the calculator does when there's no value there. That's how it deals with jump discontinuities. Less than 7, we're at +2, more than 7, we're at -2, and we're always going to be one of those two numbers. So, but as we saw on those tables, the limit as x approaches 7 from the left when we're less than 7, that was 2. And the limit as x approaches 7 from the right when we were more than 7, that's -2. Right? And yeah, that's what we have for all of our problems. So remember, I guess if you're reading this or you're listening to this and you didn't submit a problem, you really need to start submitting problems. They can be from
Here's the top Google result.
Oh, great. It can be from the homeworks. It can be from the reading. Any of the 3 sections that have to do with a week. And all weeks will have 3 sections from here on out. Yeah. So I will see folks on the next one.